really wanted to do it.
Well, you could have gone under, do it like a ninja roll.
No, do a ninja jump over. Yeah, it is. I just want to say this. Here.
You got it in? He had luck for a second there. He had luck me in there.
Now we can't talk because we're
Oh, is it recording already?
Yeah.
Oh, great. It's gonna be recorded.
Just to hear your voice.
Yeah, no kidding. No one's gonna watch the video for sure.
Yeah, especially if it has my voice and your voice in it.
Game over. One lane experiment would be bombed for sure. Be doomed for sure, huh? What's it, 26? Be careful of the corners, like right there, by your feet.
You picked the worst place to sit, and I picked the
No,
worst
no.
place to sit to.
I picked a good place to sit, it's just that he came along.
See how the shit you could put it over.
We have the same eyes.
Really good stuff.
Good morning, everybody.
Good morning.
Prime seats up.
Too close.
Any questions before we start out? Let me say one thing in response to Neil's question from yesterday. And use it to make a bigger point about what regression is all about and what regression tests are all about. If you have data that you're trying to fit a regression line to, right? Let's just take a bivariate case. And let's just reproduce these data over here. So these are exactly the same data scatters. When you run a regression and calculate a, let's say a t-test, right, for a coefficient, in the bivariate case, it's pretty easy. All you're trying to do is compare to what's sometimes called the null model, which is to say there's no relationship between x and y. That's the baseline, and the criterion is distances between each of your data points and this horizontal line, right? And total sum of squares is just taking each of these distances and squaring it, adding it up. That's the total sum of squares for the null model. The regression model that has one independent variable is going to find the best fitting line, which is a little bit too high in that way I've drawn it, but you repeat these calculations, every point deviation from this regression line. You square those distances because things work out better when you, in terms of algebra. But also it's a maximum likelihood solution to do this sum of squares. But anyway, you take the sum of squares with the same data fit to the regression line versus the flat regression line, which is in effect forcing the coefficient to be 0. And you try to see if you get a significant reduction, right? And a t-test, a test of the f-test of the r-square for the regression, those are just calculations that proceed directly from those differences in sums of squares, right? So the question Neil asked was, suppose you have Hispanic males who are observed between ages 10 and 15, their past value, versus Vietnamese males square, and they tended, no, that's not right. They tended to drop at first a little bit and then maybe go up at the end. If you actually plotted it out, it would be very hard. There's tremendous overlap in the data scatters. What that dummy variable model where you interact whether Hispanic or whether Vietnamese with the age variable, what that does is compare the sums of squares when you just take the Hispanic model, right? You're wanting to test whether the collective significance of all the interaction variables, if you shift the constant term, if you shift the age term, if you shift the age squared term, to fit just Vietnamese males relative to Hispanic males. Those are the coefficients that you have in the interaction terms. The post-test was whether that collection of variables equals 0, whether those 3 additional interaction variables added anything significantly to the regression, right? So all that's happening, and the question was, isn't it certainly going to be different because the best fitting line to the Vietnamese males was starting way up here, coming down here, and then going up there, right? And the best fitting line to Hispanic males was starting way down here, peaking just after age 10, and then starting to come down. So it looked like you had very, very different functional forms, and almost certainly different functional forms for the two groups. But all that's happening for that test is the actions in here between 10 and 15. And in effect, it's taking the fit for the Hispanic males and getting deviations not only for the Hispanic males but also for the Vietnamese males to this single line for Hispanic males. And then it's saying, how much better can you do if you add in a separate regression line for Vietnamese males in terms of reducing error sum of squares, right? And with the original line, the error sum of squares, with all the points, including Vietnamese males, is down to its original line. And then you're saying, how much better can you do if you allow for there to be a separate line for Vietnamese males and calculating residual differences for Hispanic males from their line, residual differences for Vietnamese males from their line. And it turns out that you do insignificantly better, right? The probability level for that hypothesis test was very large, much larger than 0.10, which is saying that even though there does seem to be a somewhat different shaped line, it's not significantly accounting for more of the action for the actual data. Neil, you have a question?
Yeah, I was going to say, I realized eventually it had to be bounded because any two non-parallel lines, I mean, not just curves, will eventually be different by infinity. So it had to be just between the bounds you put in. But so what you're saying is it compares the fit of the Vietnamese line to the Vietnamese data compared to the fit of the Hispanic line to the Vietnamese data.
Essentially, you have cast value A plus B1 age plus B2 age squared. And then you have this collection of whether Vietnamese, C1, C2, whether Vietnamese times age, plus C3, whether Vietnamese times age squared. Right? That was the equation that you fit, and then you tested. You can do this test in various ways. You can either test whether this collection of coefficients equals 0, You can test whether this collection of variables adds significantly to the R-square. You get the same kind of test statistic and probability level, but when you're saying, do you do better with this collection of variables? You say, well, let's start out with the original variables, see how well we do, which is to say, how well do not only the Hispanic males, but also the Vietnamese males fit to the Hispanic male line. This is the Hispanic male line. And then, how much better do we do if you allow Vietnamese males to have their own equation? And, you know, it's somewhat better. It's got to be better. You're allowing for a different relationship, but it's not significantly better. It's what the test says. Okay, is that helpful? Okay, so let's spend not very long at all on path analysis. We've done structural equation modeling with George, and in some ways have gone far beyond what I could do. But I just want to talk about the practical application of path analysis and why structural equation modeling is really just regression, using the kind of tools that you've already acquired. So the problem set problem has parent high school grad and math raw score and then task value. You know, conceptually it's not so meaningful, but it's just an illustration of a possible mediated model. It's saying that this relationship between family background and task value can be accounted for to some extent by the math raw score. So it's a prototypic kind of intervening variable. You can think about this as a SEM model, or you can think about it as just a set of regression models. And the regression models are just built up from what's being predicted by every variable that's predicted by at least something, right? So math raw score is predicted by something, so there's a separate equation for it. And then task value is a separate equation because it's being predicted by both math raw score and parent high school grad. So and then this is the mediated model. And then the reduced form total effects model, so sometimes called reduced form. Is just parent high school grad predicting task value. Right, so that's kind of the big picture, and then you're saying we might want to know to what extent that big picture, those total effects, are operating through math raw score versus independent of math raw score. And we can think about the equation, the total effects equation is just task value as a function of parent high school grad. That's this. And then we get a direct effects equation for task value, which is going to be a function of everything leading up to task value. So that's task value C plus D1 parent high school grad plus D D2 math raw score. All right, we're just taking this and seeing what's leading up to it. And then we also have math raw score as a function of everything leading up to it, which is parent high school grad. And we'll say that's E plus F1 parent high school grad. So if you want to label these paths, this path is going to be the coefficient on math raw score in the equation that relates task value to both math raw score and parent education. That's D2. This path is going to be from the same equation where math raw score is controlled, and you're looking at the coefficient on parent high school grad, which is D1. And then this is going to be the path running from parent high school grad to math raw score, which is just F1. And if you substitute, let's call this 1, 2, and 3. If you substitute 3 into 2, you can put together what amounts to the total effects equation. So you have from equation 2, task value C plus D1 parent ed plus D2. Instead of math raw score, you can put in what math raw score equals, which is just E plus F1 parent high school grad. Right? And if you expand that out and collect terms, you've got task value equals C plus D2E, which is the kind of combined constant term. Yep. C plus D2E plus, and now you have these two terms with parent education, which is D1 plus D2 times F1 times parent high school grad. Right, so now we're back to the total effects equation with task value just as a function of parent education. So whatever this total effects equation is saying the relationship, reduced form relationship is between parent ed and task value, has to be decomposed exactly into these direct and indirect effects. Right? So task value is going to be a function of, in terms of parent ed, D1 plus D2 F1. So it's this plus this times this. Right? That's what you learn right away in SEM. But with the exercises, you can see if you actually calculate these things separately and compare what you get, if you just relate task value to parent ed, you get exactly the same coefficient and constant term that you'd expect if you did these two equations separately, plugged it in. So that's showing that there's this 100% decomposition of total effects into direct effects and indirect effects. Any question about that? Is this extremely old hat? Yeah, go ahead.
So you said that, is it just the total effect model at the end when you plug in?
Yeah, this is just task value is a function of some constant, there's no variable here, plus some coefficient times parent f. And that's all this equation, which is to say this equation is. So this implies V1 in equation 1 has to equal B1 plus B2 F1, and this has the interpretation of the direct effect, and this has the interpretation of the indirect effect. Okay? All right, so what can go wrong with mediated models? Let's first do the Lee and Frank mediated model, just to make sure everyone sees what's going on. This is a same principles, but painfully applied because it involves so many different variables. So look at the diagram.
Do you have more copies?
What's that? So, all right, so thought I had way too many. I've got more than enough. Okay, everybody's all set? All right, take a look at the diagram with 182 just above it. Mediated model. It's actually not drawn very clearly because if you look at the very top line, student background, that G path, it's running through community college behaviors, but it really should be, I don't know, maybe they couldn't figure out how to make a kink line. It really shouldn't go through that circle at all. That's the direct path. That's this thing. It's not running through any of the intervening variables. But everything else is part of the mediated model. And each of these circles has a bunch of variables in it, which makes it a little more complicated. But the general idea is exactly analogous to what we worked out here. So it's a system with a number of different stages of intervening variables. And to figure out what all these paths are, you just go through the same kind of thought process that we went through in the simple model. So there's going to be an equation starting out for high school behaviors. Everything that has arrows running to it is a dependent variable in some sort of equation or set of equations. So down at the bottom, high school behaviors is going to be a function of student characteristics. That's the set of A coefficients in this model. High school outcomes is another intervening variable that's predicted by both high school behaviors and student background. That's the B and the C. Community college behaviors, a function of three preceding sets of variables, and then transfer to a four-year college is a function of everything that precedes it. All right, everybody sees that? And if you had an afternoon, you could probably crank through the equations and work out all the direct and indirect effects. You're going to get some indirect effects that have a whole bunch of terms to them, right? Because if you think about the total effect of student background on transfer to a four-year college, well, there's a direct effect, that's G. It's supposed to be independent of everything. There's a two-level indirect effect, D times H, because transferring is a function of community college behaviors, which in part is a function of student background characteristics. H comes from a regression and transfer to a four-year college on everything leading up to it. So you just pull off that set of coefficients. D is going to be from a regression where community college behaviors are a function of everything that precedes it. You just pull off the student background characteristics to get the D numbers. But you multiply those two together, and that would be the contribution of student background operating through community college behaviors as it affects transfer to four-year college. But you could also get an indirect effect of student background and transfer to a four-year college that operates through high school behaviors, which operates through high school outcomes, which operates through community college behaviors, right, which affects transfer. So that's going to be the product of A times C times E times H. So here we just had a single product, but the more levels of intervening variables you have, the more you have to multiply these things out. One sad thing to note, indirect effects are multiplicative. And therefore usually pretty small. So if I have some model like this with all the other paths in it, even though this might be a big number, these are standardized coefficients. So this is 0.5, pretty big standardized coefficient. This is 0.5, pretty big standardized coefficient. This is 0.5, pretty big standardized coefficient. Let's suppose all are significant. Even though each component is significant, the fact that you multiply them all together makes for a pretty small product, right? 0.5 times 0.5 times 0.5. You're down to 0.05, which isn't a very big number at all. So people tend to just look at the significance of the paths. Let's say we're back to a simpler model. Let's say this is 0.4. And you get really excited about the fact this is significant and this is significant, therefore there's mediation. But oftentimes by the time you multiply those numbers together, it's not very much mediation. It might be 5% mediation. People often ignore what the absolute fraction of the total effects action that you get for mediation amounts to. There's a test for mediation that you are doing this week, right? The Sobel-Goodman test, which is a formal test of the extent to which mediation is significant, statistically significant. Again, I think there are two ways that people think about mediation. One is there significant mediation? That's usually the question that people get really obsessed about. But then there's another question. how much of the action do the mediators account for? And those are quite distinct questions. And I think both are important. Let's say you've got a system with a simple mediator. The reduced form, let's say, is 0.50 with a standard error of 0.20. Quite significant, more than twice the standard error, right? Now let's say you do the mediational model.